Hello and welcome to part 3 of the Advanced PIM Sparse Mode lecture in the IP Multicast lecture series. In part 1 of the Advanced PIM Sparse Mode lecture, we covered the join process in detail, and that had to do with the LHR joining the RP on a star comma G tree or a shared tree, and the RP joining the first hop router on an S comma G tree or a shortest path tree. In part 2, we covered the registration process that happens between the first hop router and the RP, thereby enabling the RP to carry all of the information about all of the active sources, where it can then bring all of the receivers from the last hop routers and join them to the sources that are connected at the first hop routers. To bring the series to a completion, we discussed the phenomenon of the shortest path tree or the SPT switchover today. This is a process that happens at the LHR as it starts receiving some packets over the star comma G tree from the RP. Once the LHR receives that very first multicast packet, so it is now on the star comma G tree, up to the RP, and RP has joined some sort of S comma G tree, or maybe it received a register message that had an encapsulated packet in it. Whatever were the means of that, there is a multicast packet now following the star comma G tree, and it eventually reaches an LHR. So LHR, where there were IGMP joins or IGMP membership reports from the receivers. This first message, this first multicast packet, as it is processed by the LHR, provides the LHR some very important information. So remember the whole reason for having a rendezvous point in sparse mode. The reason was that the LHRs, or the last hop routers, are not aware of any sources to begin with. They're aware of all of the interested receivers. So the interested receivers either used IGMP signaling, or there is some sort of static signaling or static configuration that is going on for the groups. It knows the groups it needs the multicast packets for. It has no idea of the sources it needs them from. And that is the whole crux of any source multicast. So you need it from any source at all possible. As that first multicast packet comes down the stream and it is processed by the LHR, the most important piece of information that is acquired by the LHR is that it now knows a source that is sending to that multicast group. So this is some previously unknown information. This is the information about that S that it did not know before and that it really needed the RP for. So for this particular S comma G stream, so the S comma G stream that is coming from this particular source, if you think about it, the LHR no longer needs the RP's help to connect, because it now knows the S comma G tree, and we have this join prune mechanism, remember, for the S comma G. So this is the same mechanism that was used by the RP initially after the registration process. So really, the S comma G join process depends on the knowledge of a source. The RP acquired this knowledge using the register message. So the FHR sent a registered message to the RP, and thereby the RP acquired the S comma G information. The LHR acquires this information from this very first multicast packet, but the effect is the same. They're both, RP and the LHR, are now aware of a source that is sending to the stream. So they have complete information for the S comma G stream. And what it can do, what the LHR can do, is it can do the exact same thing that the RP did. It can initiate now an S comma G join towards the FHR independently of the RP. So the RP may be an MHR, a middle hop router in this process, but it really is not bothered. The LHR is not bothered about the RP anymore because it has this independent information. So it can just simply send an S comma G join towards the FHR and create a shortest path tree of its own. So it does not necessarily need the RPT or the star comma G tree to receive the stream from this S comma G anymore. And that is the whole crux of the SPT switchover. Once the signaling completes itself, so the S comma G goes completely from the LHR to the FHR, and the LHR starts receiving packets on this SPT, the SPT switchover then is complete. So what are the motivations for this, right? Why do this in the first place when we went through so much pain setting up an RP, setting up the FHR, setting up all of these other mechanisms? Why perform the switchover now when we are really receiving the packets down the star comma G tree? And that's a valid question. There could be a scenario where the RP might not actually be on the shortest path tree. So the RP, the tree, when you look at, and we will look at it, look at this particular phenomenon in some detail, but it could be that the shortest path between the FHR and the LHR does not really pass via the RP. The RP could be way, way far away, maybe multiple hops away. So sending all of the multicast packets first to the RP only for the RP to relay them onto the star comma G tree may not be the most optimal path between the FHR and the LHR. So really the main motivation for the S comma G or the SPT switchover is to create the most optimal multicast path between the first hop router and the last hop router. Having said this, most implementations, many that I have seen, they practice what is called a first packet switchover, where the moment they receive that very first multicast packet, they initiate this S comma G join, and they do not bother finding out whether the RP is in fact on the optimal path, because RP is just another router in the network, right? So it could be on the most optimal path, you have no idea. But regardless of that, they do practice the first packet switchover, and they'll just create an independent S comma G tree regardless. So the moment the source is known, the very first moment, they initiate this S comma G tree, and they'll keep both of those star comma G trees and the S comma G tree simultaneously. Now, if the RP happens to be on the S comma G tree, and once again, we will see this, it'll make much more sense once I go to the actual topology. But if the RP happens to be on the shortest path between the LHR and the FHR, so it's really another router on the S comma G tree, what it can do now is it does not have to do that replication from the S comma G to the star comma G anymore. Because now the S comma G is one continuous tree that just passes through the RP. So again, I'll defer to the actual slides that are coming to show this, but really the RP is not replicating packets anymore. It really just has a complete S comma G tree with an IIF and an OIL, and it just receives the packet on the S comma G, sends the packets out or forwards the packets out on the S comma G. It's not replicating packets from S comma G to star comma G anymore. And for this, if you look at the outgoing interface list, the OIL, it will match. It'll match between the star comma G and the S comma G. So really the decision's up to the RP of what to do with it, but it does not have to replicate per se anymore, not for that S comma G, because the S comma G now passes through the RP itself. This is the same completed scenario that we have looked at a couple of times before in the previous 2 or 3 lectures. And ultimately what's happening here is that the S comma G tree is complete from the RP, which is R3 in our topology. And from the RP or R3 to R1 or the FHR, the S comma G tree is complete. And from the LHR, which happens to be R6, to the RP R3, the star comma G is complete. So as the source, S, in this topology, sends a packet to the group G, R1, R2, and R3 will process them on the S comma G tree, RP will replicate them from the S comma G to the star comma G tree, and ultimately R6 receives this packet. Once R6 receives this packet, it can now create an S comma G tree. So it really has the information to create an S comma G tree out on itself. So R6 will create an S comma G tree here. Once it creates this S comma G tree, it now will initiate an S, G join. So that maroon line is an S, G join that is being initiated by R6. R4 happens to be just another router that is processing this S, G join. And remember now, this is not a star, G join. The star, G join, the RPF check on it is based on the RP's IP. The S, G join carries the actual IP of the source. So when R4 processes this particular message, for example, it can choose another different link. So as this message comes in, the very first thing that R2 is going to do, or R4 is going to do, is to add this interface to the oil. Actually, even before that, it's going to create the S, G. So once it creates the S, G, right here, it'll then add that interface to the oil. Now it is going to perform an RPF check on that source. And for example, maybe for speed reasons or maybe for the way the unicast routing is, think of it as if it comes up with this particular interface as the RPF interface. So between R4 and R7. And now this becomes the IIF for the S, G tree. We've seen this in the previous 2 lectures at length, so this should not be new, right? Now R4 will send a S, G message, an S, G message towards R7. And R7 will now do the same 2 things. It'll create the S, G tree. Once it creates the S, G tree, it will then add this interface between R4 and R7 to the oil. It'll figure out an RPF interface, which there's only one interface going towards the source here, which is R7, R2. And this interface then becomes the IIF. And once all of that information for the tree is complete, R7 will send an S, G join over to R2. Once it sends this S, G join over to R2, R2 actually already has that S, G tree. So in our case, because of the RP's signaling of the S, G, it's the same signaling that is coming from R7. So R2 already had these 2 pieces of information. So R2, because of R3, the RP's S, G, it already had the IIF, and it already had one interface to the oil. As it receives an S, G join from R7, it'll simply just add one more interface to the oil. So it already had some information, and it just updates that information with the oil. But now, as you can see, there is an SPT that now goes from R1 towards R2, down to R7, towards R4, and finally down to R6. So this is completely different from the RPT, which went from R6 to R4 towards R3, and then continued on towards R2 and R1. So depending on the topology, the SPT and the RPT-SPT combination could be radically different. Sometimes, and this is again, it comes to troubleshooting, sometimes one part of this tree may be working perfectly, but another part of this tree, for example, out here between R2 and R7, you may not have PIM enabled on this interface. So what would happen then is, as long as you're receiving the packets on the star, G, everything works fine. And once R6 performs that SPT switchover, because of this missing link, you just lose all of the multicast connectivity. So this would usually, you would see it as the first few packets of the multicast stream being received on the receiver. So initially you receive some packets on the interested receivers, but then all of a sudden there's nothing, it's complete silence. So that's a pretty good idea that the SPT switchover took place, and then there was something wrong with that SPT. But to know the SPT switchover enables you to then move your troubleshooting efforts in a different position, because you don't really need to even look at the RP anymore. The RP is doing its job. You're receiving those first packets. So you need to know this in order to focus your troubleshooting at a different place. Once the SPT switchover is complete, so that S, G tree signaling from the LHR to the FHR is complete, you're really faced with two different scenarios. And one of those could be that the RP is not on the SPT at all. The SPT between the LHR and the FHR is completely different from where the RP sits. But oftentimes, and especially small networks, you may find that the RPT is actually on the RP, the rendezvous point, is actually on this new SPT as well. So maybe RP is so central that everything sort of passes through it. In this case, now if you look at it, the S, G tree, the SPT, is now congruous with the star, G tree. So in this particular, because of that first packet switch over phenomenon, where basically the implementations are not really bothering to find out whether the RP is on the tree or not. They're simply signaling the S, G tree the moment they receive the first packet. You would see two very unique things. So you would see that there is an S, G tree that exists all the way from the FHR to the RP, and then the RP to the LHR, because the RP just happens to be in the path. What the RP is now doing is it's basically adding an extra interface to the oil of the S, G it already had, whereas previously it may have been a stub tree with no exit interfaces. Between the RP and the LHR, the star, G and the S, G, they share all of the interfaces. So all of the IIFs and the oils should be completely similar to each other. They should be an exclusive set of interfaces between the RP and the LHR. So there is redundancy in the control plane here, because remember, PIM is a soft state protocol. You have to re-signal the star, G and the S, G joints periodically, 3 minutes or so usually, but you would be now doing it for both of them. So in the control plane, this is not good redundancy, this is just redundancy. Both star, G and S, G joins will be initiated from the LHR on a periodic basis. So star, G towards the RP, the S, G towards the FHR, and on all of the MHRs, so the middle hop routers that exist between the RP and the LHR. So in our case, if you look at the previous topology, that was R4. They would have both the star, G and the S, G states. And furthermore, both of those states would have the same incoming interfaces and the same outgoing interface list. But that's just the extra signaling that is happening here. So redundancy not in a fault tolerance kind of way, redundancy in just extra signaling in the control plane kind of way. There is the forwarding plane itself. So if the forwarding plane usually has nothing to do with the control plane. Once the signaling has taken place, you've acquired all of the information. How you forward the packets, it's implementation specific. So for example, one of the implementations that I came across, it processes all of the star, G traffic. So as the traffic comes from the multicast source S on multicast group G, it only processes all of that traffic after the SPT switchover using the star, G forwarding state. So it does not use the star, G forwarding state anymore. It only uses the S, G forwarding state. What it is using the star, G state is only for new sources that may show up. Because remember, there could be multiple sources that are sending to the same groups. So the RP needs to keep that star, G state fresh for those sources. But for the known source, the S, G, it's only going to use the S, G forwarding state exclusively. So one of the ways this would manifest, if there are no other sources, S happens to be the only source in the network. If you look at the packet count on the star comma G tree, it never increases, because really the RP does not have any need to forward any of the traffic on the star comma G, because all of the traffic from the sole known source is now being forwarded on the S comma G. So once again, the forwarding plane itself is implementation specific, but the troubleshooting hardly ever involves the forwarding plane. The troubleshooting would always involve the control plane, and that's where you would find these parallel trees that exist between the RP and the LHR. So signaling wise, when the RP is on the SPT, so for the meanwhile, I've just taken R7 completely out. There's just a single tree or single set of links that exist between R1 and R6. In this case, the LHR does exactly the same things as before. It signals that S comma G tree towards R4. R4 creates that state, and R4 signals the RP creates that state. But now there are two parallel trees between the RP and the LHR. There's a maroon tree and there is a star comma G tree, so the green tree. Now, if you look at the multicast traffic flow that was taking place before the SPT switchover, so this is just a signaling. Now we are going into way back time where there was no SPT switchover, or this is maybe the first packet. So the registration is now complete. The source is sending that first packet. And this, again, we've looked at it before, but just to refresh your memories, this is what would happen. R1 will send that packet towards R2. Now this is going on the S comma G tree. R2 sends it to R3 again on the S comma G tree. But the R3 being the RP has a stub entry for the S comma G tree. That just means that there is no oil on that tree. There is no outgoing interface list. Because what the RP really does in theory, now this is not forwarding plane. The forwarding plane is much more efficient than this. But what is happening in theory in the control plane, or from the control plane point of view, is the RP then relays this packet from the S comma G to the star comma G, and there it carries on its merry way on the oil of the star comma G. So it goes to R4, R4 sends it to R6, R6 sends it to the receiver. This was the traffic flow theoretically before the SPT switchover. Now again, this may be much more efficient than it looks in the forwarding plane, but from a theoretical point of view, this is sort of inefficient. You're taking packets on one tree, relaying them on another tree, and troubleshooting wise also, it can be a bit of a pain. After the SPT switchover, so now we're going back to our slide where the signaling now is complete. So if you look at the maroon arrows, they are complete from R6 to R4 to R3 to R2 to R1. So there are two parallel trees, but from an RP point of view, there is, from an SPT point of view, there is an end-to-end SPT. Now, the RP can simply forward the traffic down the S comma G tree. So the whole charade of copying packets from the S comma G and relaying them on the star comma G, that doesn't even have to happen in theory, because what would happen here is R1 sends a packet to R2, R2 sends it to R3, R3 is now receiving this packet on the S comma G state, which is no longer a stub state. It actually has an oil, and that oil happens to be this interface between R3 and R4. So it can simply just replicate that packet from a multicast point of view on that particular oil, and out it goes over to R6 and over to the receiver. So you can see from the perspective of multicast forwarding, also multicast control plane, this is much easier to troubleshoot because now you're just troubleshooting a single tree. From the point of view of forwarding plane, I'm really not sure if it's any more efficient because everything is done in hardware anyway on these routers. They're super efficient. So the whole idea may look a little bit complicated, relaying the packets from the S comma G to the star comma G, but in reality, it may happen just as fast as this because the hardware logic of this doesn't really change at all. The other scenario could be the RPT is not on the SPT at all for that particular multicast stream. So the tree, instead of being congruous now, is incongruous. The S, G is not exactly the same as the star, G. Now what would happen is the S, G simply exists from the FHR to the LHR, just like we saw earlier. So that particular tree, the S, G, there is no RP on that tree. It just simply exists from the FHR to the LHR with a bunch of middle hop routers. The star, G, however, still exists from the RP to the LHR. And this really needs to exist for any of those new sources. So S being one source, what about S1, S2, S3? For all of those sources, it's any source multicast. So the LHR theoretically may need packets from all of those sources. So that star, G still has to exist as a placeholder. It just is not really responsible for switching S, G. S being a particular source, call it S1, whatever you have. It's not responsible for switching that traffic anymore, but any new sources that show up, it will switch their traffic. Now there is redundancy in the control plane until what I have called, now this is just my term, you may not find it anywhere else. There is redundancy in the control plane till the bifurcation point. And what I am calling the BP or the bifurcation point is the first router where the SG or the S, G deviates from the star, G. In our topology earlier, this was R4, where the star, G went towards R3 up to the RP, but the S, G went leftwards towards R7, and that was the shortest path to the source. So bifurcation point, this is the first point where the IIF, if you think about it, of the star, G and the S, G differentiates. It's not the same IIF. For the LHR, so the LHR is unaware of this. It's simply joining both of those trees. So from the LHR, you would see that there are both star, G and S, G joins that are initiated. Both star, G and S, G states will exist on all of the MHRs between the bifurcation point and the LHR. Now in our topology, there are no such MHRs because it's a small topology. But all of the MHRs between the bifurcation point and the LHR, they have the same IIF, again, for the star, G and the S, G. So they will keep both of these states. They'll keep the star, G state, they'll keep the S, G state, they'll keep the same IIF, and they'll keep the same oil. However, at the bifurcation point, which is the first point where the S, G and the star, G have different IIFs, there are significant changes, and you really need to understand this in order to not be burned by this. The star, G, that doesn't change because there is nothing significant that is happening from a star, G perspective. So for star, G, it exists just as usual. So those joins are sent as usual and they're sent towards the RP. The S, G joins, they are now sent towards the RPF neighbor for the source. So this is where that IIF is now completely different. So once again, the S, G joins, they are sent towards the RPF neighbor for the source. So star, G, RPF neighbor towards the RP, but the S, G is towards the RPF neighbor of the source, that S. If you realize there's really no need for, you need to tell the RP somehow that it is not really needed anymore for this particular source, because you're going to receive, beyond the bifurcation point, you're going to receive the stream from the source independently on the SPT. So you really don't need to keep receiving that stream on the RPT, because RP still has its own S, G. You still have an star comma G from the last hop router to the RP. And because of that, you may start getting 2 copies of it. So you need to tell, the bifurcation point has the responsibility to tell the RP that you don't need to send the stream for this particular S comma G, this particular source on the star comma G anymore. And it uses a special type of prune, special type, completely new, called the S comma G comma RPT prune towards the RP. And what this is saying is prune the S comma G entry. So keep the S comma G, this particular stream, in a prune state only if you are an RPT. So remember those wildcard bits from lecture, well, part 2 of this lecture, I forgot, or part 1 of this lecture, where we discussed the joins. In that particular lecture, I stressed on the WC bit and the RP bit. This is that RP bit now just being turned on. So what you're telling is, you're telling the RP that prune the S comma G only if you're an RP. Nobody else needs to prune it. Only if you're an RP, prune it. And once the RP receives it, it's a special prune, and it tells the RP that the RP no longer needs to be on the S comma G tree. So not at least on behalf of the bifurcation point and the router south of it. So if there are some, it's a very complex topology. What this means is prune the oil that is going towards the BP, prune it out and do not send any more S comma G stream on it. At the same time, this is an S comma G prune for a specific reason. At the same time, the RP needs to keep the star comma G state intact. Once again, for the new sources. Now, if this has caused complete confusion, the next set of animations will actually make this much, much better. But this is theoretically what is happening. As we saw earlier, R4 in our particular topology happens to be the bifurcation point. And why is it the bifurcation point? It's simply because of the choice of the IIF. So if you look at the star comma G tree, what is the IIF for the star comma G tree? Why, it's going to be the RPF interface towards the RP. So the choice is very simple. That green interface there happens to be the IIF for the star comma G. It's also the RPF for the RP, which is why it was selected. For the S comma G tree, suppose this link between R7 and R4, suppose it happens to be a 10 gig link, whereas all of the other links are 1 gig links, just to simplify it radically. If you look at the unicast routing table, R4's shortest path to the S, the next hop, should be R7. So it should also become the RPF interface. And because of that, it should also become the IIF for the S comma G tree. Now there is a clear bifurcation here because the S comma G is no longer congruous with the star comma G. They take different paths. So because of this, now R3, the RP doesn't really need to send the traffic. Remember, it was replicating all of that traffic between the S comma G and the star comma G, and if that traffic was to come down to R4 would just now get 2 copies of it, and that's inefficient. So what R4 would now do is it will generate that S comma G comma RPT prune. So look at the legend towards the very, very bottom left. You'll see that bright red is the S comma G comma RPT prune. And what that tells R3 or the RP is to, number one, delete the S comma G state. So look at that S comma G state. It's now gone. So it was there before. And at the reception of that S comma G comma RPT prune, R3 realizes that it is the RP. It's now gone. Furthermore, there is an S comma G state between R3 and R2 because it was signaled on behalf of the R6, the star comma G join before. That is no longer needed. So R3 will further prune itself off the S comma G tree. So now that link is pruned, and now the topology is much more efficient. There is an S, G tree that goes from R1 to R2 to R7, sideways to R4, down to R6. And for any newly discovered sources that may register itself at the RP, there is still that star, G tree that goes from R3 to R4 to R6. So you're covering all the bases here. You're covering all of the new sources that may appear, but you are efficient when it comes to the already discovered source of S. That brings us to the end of part 3 and to the end of the Advanced PIM Sparse Mode lecture. We will see you again with a brand new lecture. Please leave any comments, any criticisms, any questions that you may have. And thank you for watching this lecture.